So I don't normally do this here, but I don't feel like we could actually cover a lot of like new or interesting stuff in this video. So I'm gonna put a quick disclaimer here. This is good kind of as a quick general overview or refresher of some of the material we've covered around the Poincare-Birkhoff-Witt theorem, but if you're comfortable with those videos, this probably isn't worth the time. I'm just putting it here for like showing that I did put in the time myself. Enjoy, potentially. So, hello and welcome back, and today we're continuing, probably finishing off or getting close to finishing off our redux look at the universal algebra. Today we're covering a few things. Our first one is theorem 4.3, which you may recognize as the Poincare-Birkhoff-Witt theorem. It says if G is a key-free module, then the map I, which we defined yesterday as the canonical homomorphism from the symmetric algebra of G into the graded universal algebra of G. I'm going to show that this is an isomorphism. And as before, we need lemmas and going forward we're gonna let xi indexed by indexing set I be a basis of G with a total ordering on, I guess, I or the basis itself, same thing really. One gives the other easily. So, our first lemma, the family of monomials of ascending basis elements, the image of ascending basis elements in our universal algebra where we have m copies of our lower value, and generate u to n g for this m less than the n of the size of our universal algebra. I kind of chose bad n there, but whatever. Proof by induction is by induction with n equals 0 occurring automatically. Suppose it holds for n minus 1. Take a in un of g. Then the graded version of a is a polynomial of degree n in the images of x di all the way forward, and so is a linear combination. Of some of these epsilon exi, I'm going to index them with j this time is better, plus an element a1 in the previous g. But by induction, by the induction hypothesis, a1 is equal to some linear combination is the sum of some linear combinations of these basis elements in ascending order. And yeah, so there we go. So this says that the Poincare-Birkhoff-Witt theorem is equivalent to the statement that this family of binomials is the product of E xij in ascending order, to saying that, I'll put it in quotation marks, it's kind of weird, but is a basis of the universal algebra of G. And a similar idea for ascending sequence M, we write x to the m be the product of, that's not how you do the product, of the images of these things, and we note that the length of m as the L of m equals m. For each n of least 0 in natural, the xm with m having length n lie in u sub n of G, with images xm bar in gr n of ug, which, reminder, is u n of G mod u sub n minus 1 of G. And these are also the images under the map which we're looking at, I from Sn of G to gr sub n of u of G of the monomial basis elements of Sn to the G. Thus, I is injective is equivalent to saying there does not exist a linear combination of Cm xm congruent to 0 mod u n minus 1 of G. The length of M is n for some non-zero Cm. And we can turn this formula into the sum end of the length being exactly equal to n from the previous lemma into the length of m must be less than n. Alrighty, and then everything will reduce. Alright, so back to the Poincare-Birkhoff-Witt theorem in the new form. Maybe, or maybe there's one more detail. So we're going to let V be the free K module with basis of these xm with m being the set of sequences of ascending sequences in our index I, indexing set I. And as last time, we say that an index is less than some m, less than or equal to some m, if for all m in M, I is less than or equal to that index. With then being putting at the start. So essentially, we only need to actually check for the first element. Then m continues as before. Here's our main lemma. We can make V a G module such that x to the I times z to the m is just z to the I m for I less than or equal to m. So we define a k-linear map oh, it's bilinear. Just remember that. I don't want to go back and fix it. As the from x and v to xv, that is not even legible. Xv of where x is from G and v is from our module v into v. It makes v a G module So to define our xv, we define x sub I, z sub m for all I and m. And to define xi zm, don't even need to write that down. We assume by induction that x sub j z sub n has been defined for all j in I when the length of n is less than the length of m, and j is less than I. No, this is actually separate, and when j is less than I and the length of n and m are equal. And we do this such that x sub j z sub n is a k-linear combination of ZLs with the length of L less than or equal to the length of n plus 1. So we then put x sub I z sub m to be equal to, I should give myself more space for this. I'm going to write these out of order so I don't run out of room. So it's going to be equal to just ZIM if I is less than or equal to m, and this bottom term if m is equal to jn with I greater than or equal to j. Once again, j is just peeling off the bottom term of m with the remainder of n. Now, since both sides, oh, hang on, we already have that. Sorry, one sec, I gotta figure out where we're heading here. All right. And we see that this satisfies, I'm just going to say this satisfies the conditions. I'm kind of realizing here this is not really going to give us any new insights necessary for this video, so I'm going to kind of do this, which I know is kind of lame, but like I said, I didn't get a chance to vet this properly beforehand. I feel like we've already proved this, so yeah. It's worth noting we have in set V the element of Z naught. So for all m, we have that x sub m z sub naught is equal to z sub m. We show by induction on the length of m, we have our base case, of course, automatically. So if the length of m is greater than 0, we split off the lower element of m, so then x to the m is x sub I, x sub n, and x sub m sub naught is x sub I, x sub n z naught, which is x sub I, z sub n, which is by definition z sub I n, which is z sub m. And again, we need to suppose we have the sum of c sub m x sub m equals 0. And then 0 is the sum of c sub m x sub m z sub naught, which is c sub m, which is the sum rather of said c sub m with z sub n. So we have linear independence. A couple corollaries again. If G is a free K module, then the injection map from G to UG isn't, I guess, calling it an injection map is not right, because this is a condition that needs to be injective. And G is actually isomorphic to GR, the first grade of universal map of G. Second corollary here. We're going to split G into the sum of G1 and G2. With each being a subalgebra, obviously, and also free as a key module. Within the map from UG1 tensor UG2 into UG by U1 tensor U2 into U1 U2 is a K-linear isomorphism. And see how they prove it. We're going to let xi in indexing I and yj for j in j be bases of G1 and G2. With that is not legible. It's an order, a total order, sorry, of I union J, such that I is less than J. Of course, we have bases of the form of some ascending sequences, and likewise for the other side. And we have a basis of the universal algebra of G itself as this product. I'm going to be writing pretty messy because this is what we've seen before. UG1, UG2, and UG. Thus, the given map is a bijection. Notice this induces an isomorphism from the graded universal of G1 and the graded universal of G2 into the graded universal of G. And that is because graded universal of G1 of Gi actually was for both obviously is a symmetric of Gi, and the graded universal of G is equal to Sg, which is the symmetric of the components. Tensored together, of course. What I'm going to do actually, this is something a little unorthodox. I don't feel like we've covered much new ground, so I'm gonna put this as a video as kind of like a recovering stuff here lazily. The recovery of Poincare Birkhoff-Witt theorem wasn't exactly a whole lot of new stuff. And I'll do another video proper going over our one new concept, because I feel like there's a good reason to skip over all this, which I will put in as an intro. Yeah.